Hello, this is the demo of my custom FPGA video card IP that I built. And it acts as an AXI slave, where the AXI master is the Microblaze SoC IP from Xilinx. And it uses dual frame buffering in order to do hardware rendering of all of these sprites. And to really best explain this project, I'm going to power off the board and power it back on so that we can see what's doing what. So as I reflash this project to the board, the first thing you'll notice is that just the background is scrolling. And the reason why this is important is because it shows that the CPU hasn't actually booted yet, and so it can't issue out commands to draw the other sprites. So just for that small period of time, just the hardware was rendering the background. Now that the CPU has been initialized, it can issue out these commands to draw the rest of the sprites. And it's really nice because we're drawing each of these ships, and it takes about 18 microseconds to draw a ship and about 1.6 microseconds to draw a projectile. And at 640 by 480, 60 frames per second, it takes about 16.7 milliseconds to render an entire frame. So we have so much time to draw all of these sprites per frame. And it's very smooth because of this dual frame buffer. The sprites essentially sit over the background, and they have transparent edges. So when we're over a pixel, when the beam is over a pixel that would be transparent, it instead elects to draw the background. So that's why we have this moving background so nicely in the hardware. And so the software portion is C++ done in Vitis, um, and it's only about 21 kilobytes, which is very nice because, for context, the Hello World in C in Vitis is 10 kilobytes just alone, with nothing else. And so with the optimizers, we can get the C++ code to be very condensed down. So then we send those AXI for light instructions to the custom IP, which receives them and outputs HDMI. And essentially, we're sending instructions for which sprites we'd like to draw, and the hardware streams out the ROMs for those sprites and adds them to the double buffer. And so um, we actually draw this out at 320 by 240. So what that means is I need to do column and line doubling to get this to 640 by 480. And the reason I did this is not because of anything specific outside of the memory size. Now I can't actually have enough VRAM room. I only have 2.7 megabits of VRAM on this Urbana board, which means that if I want to uh, use a double DRAM like I do for these frame buffers, I need to make it smaller. So I instead opted for 320 by 240 with doubling, and I use actually only a quarter of the memory because the height and width have been shrunk by half for those VRAMs. So that's why it's outputting so nicely to 640 by 480. I just wanted to mention that memory constraint. And now for the demo, I have actually exposed some of the onboard switches to show some of my favorite features. So the first one I want to show is that I actually don't even have to scroll at all. It's very nice uh, to just be able to, at the push of a switch, not have to scroll. And so, if I want to scroll again, then I simply just have to take this switch. So that's pretty cool. And another really fun thing is I didn't mention this earlier, but there is a dual frame buffer, and I have to clear the contents at some point. Now, in this project, I've actually elected to just dynamically do so. So as I read out the contents, I zero the line before. But if I don't do that, then we can see that we get actually quite a bit of tearing. And not all of these things actually tear equally because the sprites have their bounding boxes as transparent. you can see the sprites actually clear themselves naturally a little bit, but part of it is touching the edge of the sprite box, and so that portion still bleeds onto the frames if we don't clear it. Now I'm going to turn this back to normal because it's not very nice to look at. Another thing I really want to show is that I can easily change the scroll direction. So really that's just at the flip of a switch. We can scroll forwards or backwards, and I can also change the scroll speed. So this is going slightly faster. This is, I guess, warp speed, if you want to give it a name. It's very fast. Um, and again, this can be changed. I can, quickly change forwards and backwards here. You might not even be able to tell it's forwards and backwards. Oops, that was the wrong switch there for a second. And yeah, then I can um, also show the bleeding at a faster speed there. Um, but yeah, so those are all of the features that I exposed just to be able to show that the rendering is all done in hardware and very efficiently. And so some other things is I don't even do a single multiplication anywhere in the hardware. All multiplications are reserved for the software portion, and then I do linear computations in the hardware, and that saves a lot of time in the worst negative slack. I actually have a good worst negative slack. I render within the 10 nanosecond allowable period by I think about 2 nano. So that's nice. It allows me to just divvy up any of the, intense computational workload to the software, which is, much better. I don't have to invoke any extra hardware on the FPGA side for things. I can just basically do adders. So that's very nice. And yeah, I also wanted to just mention that if you check the C++ code, you'll see that there's keyboard polling if you wanted to, using this USB transceiver. So if you wanted to like map WASD or space to some keys for some movement and some shooting, it could be done easily. And I also have some collision detection. So, you just have to check the four corners of a sprite in order to do some easy collision detection. So I can easily just say if a projectile has hit another sprite, and then maybe I could stream a ROM of, an explosion animation for that sprite. So the point is, this is a very flexible project. You could essentially swap out the ROMs that you wanted to render and get an entirely new project, provided you also swapped out the background. You could, quite easily make it scroll horizontally if you wanted to do so. I didn't choose to do so for this project, but adding features to this video card is very easy. And I think that's what makes it so cool is once you have the end-to-end rendering, there's a lot of potential for future additions, and you could really make this a standalone video game, which I opted not to do because instead I wanted to illustrate the hardware power. But yeah, that's very easy. Anyway, that's all I wanted to show. Thank you for listening.